from HC Verma also, as I've advised you in the last lecture. So if you have started with the questions, yes, I will share the recording, Vashisht, and the notes. Okay. Yeah. So if you have worked out some questions from HC Verma from the spring mass type of systems, etc., and if you have any doubts, then maybe in the second half of today's lecture, we can pick up some of the doubts from HC Verma simple harmonic motion also. Anyhow, so let's begin. So we were looking at simple harmonic motion of spring mass type of systems. So let's continue with that today with some more examples. So we saw that essentially what happens in spring mass systems is that we get an equation which is like this, that d2x by dt square is equal to minus omega square x, where omega square comes out to be the equivalent spring constant divided by mass. So equivalent spring constant. In case of combination of springs, if it's a single spring mass, then it's just a spring constant. And from that we get the standard equation of SHM, where omega is square root of equivalent spring constant by mass. So time period becomes 2 pi under root m upon k equivalent. Okay. And of course, amplitude and phase constant come from the initial conditions. So this is the standard method that we apply everywhere for these type of systems. So let's start with an example problem today. So we'll take an example of a vertical spring mass system, but having a combination of two springs. So like this. So given that the spring constants are 6 newtons per centimeter and 12 newtons per centimeter, and the mass of the block is, let us say, 1 kilogram, and take G as 10 meters per second square. So first of all, find the time period for vertical oscillations. The block. Okay. Secondly, if at time t equal to 0, the system is released from rest with both the springs in the relaxed state. Then find amplitude of SHM for the block and find the maximum extensions of each spring in the case of second part. So let's work out this question. It's directly based on the last example we had done in the previous lecture. Let's minimize this a little so take down the whole thing. Okay, yes, very good. That's correct. Time period is, just make sure the units are clear. Okay. So again, use this formula. Equivalent spring constant divided by mass is the value of omega square. And remember here, it's like a series combination of springs. Okay, so the formula will be K1, K2 divided by K1 plus K2 for equivalent spring constant. Correct. Yes, amplitude is also correct. Okay, only for your time period, but it's the time period you giving is not going to be in seconds. Okay, because you have not converted to SI units for spring constant. Yes, Kanishk, your answer for time period is correct. But amplitude of the blocks SHM is not correct, and also you have to give the maximum extension of each of the springs, not the maximum extension for the combination of the springs. That will be the sum of the maximum extension. You have to give for each of the springs. So let's look at the first part of this question. What you can do is you can take this combination of springs as equivalent to a single spring. So K equivalent for the single spring is so now you can see that for this vertical spring mass system, omega square is K equivalent by M. So it is 4 into 10 raised power 2 newtons per centimeter divided by the mass, which is 150. Omega is square root of 400, 20 radians per second. Time period is this is the first part. So I'm not showing the derivation of this formula once again because we've done that in the last lecture. We've seen the vertical spring mass system. We had seen that if you have a vertical spring now at equilibrium position, equilibrium position extension is mg by k. So therefore, if you displace the block, let's say y downwards, then the extension now becomes like this. X here becomes, yeah. So when we solve this equation along with this, we get so this is your SHM with omega square equal to k by m. So this standard derivation I've used over here. Directly I've used this over here. So we don't need to do the derivation every time. Okay, we know that a vertical spring mass system behaves like this, so we'll make use of that. So that's the first part. Okay, now work out the second and third part. Okay, now see, to understand the amplitude and phase constant of the SHM and all, let's start with the equivalent spring first, then we'll convert it to the actual combination. So here what is happening is, if we see at t equal to 0, your equivalent spring will be at its natural length, because the individual springs were at their natural length. So when you release this at t equal to 0 with initial velocity as 0, this will immediately start accelerating downwards at g, because the tension in the spring is 0. This is what is happening at t equal to 0. Okay. But then the equilibrium position is somewhere here, let's say. So at this position, let's say the spring's extension is this much. The acceleration is 0. This is the mean position. So at this stage, so x of the equilibrium position is mg by k equivalent, which is 10 newtons, right, divided by 4 newtons per centimeter. So it is 2.5 centimeters. So if you see, with respect to the equilibrium position, the initial position is above by a distance of 2.5 centimeters. So ultimately, that's why that will become your amplitude. Okay. So now it depends on what we are taking as our SHM term. If we are taking the downward displacement as a SHM term, then the initial position will be written with a negative sign. So in general, if we are taking this as our the downward direction as our y-axis, and this is our y equal to 0 position. So from here, so when it's here, it is at L plus x, where x is equal to equilibrium position plus y. So you can see that kx will dominate over mg. It will have an upward acceleration a. So if you connect this equation with this equation, get the SHM equation. So from this you can see that at t equal to 0, in my system, I'll have to take y naught as minus 2.5 centimeters, because I've taken the y-axis as downwards, okay? And v naught is 0. And from this equation, I know y is equal to some amplitude into sine omega t plus phi, where y is the downward displacement from the mean position. Okay. And omega was this, which we had seen was 20 radians per second. So now from this information, I will come to know the phase constant and this thing. So this phase amplitude will come out to be 2.5 centimeters. So this will come out to be minus pi by 2. Again, why it will come out to be minus pi by 2? Because y naught, which is e sine phi, is minus 2.5 centimeters. Okay. And v naught, which is a omega cos phi, is 0. So cos phi is 0 and sine phi is negative. So this means that phi is minus pi by 2. So from this I can see that y as a function of time will become 2.5 centimeters sine of 20 pi t minus pi by 2, or minus a cos omega t, where a is not 20 pi but 20. So once I know why is this, so from above I can see that at any instant x is equal to this plus y. So the equilibrium value of x was mg upon k equivalent. So it was 2.5 centimeters. So the extension at any point of time is 2.5 minus 2.5 cos 22 in centimeters. So the extension of the spring is a function like this. So from this you can see that x ranges between 0 and 5 centimeters. So it is 0 at t equal to 0, capital T, so on and so forth. When omega t becomes basically 2 and 5, and it is this at t equal to capital T by 2, 3t by 2, 5t by 2, or in general 2n plus 1 t by 2, when omega t becomes 2n plus 1 pi. Okay, so from this you can see that the maximum extension for the combination of the springs is 5 centimeters. So individually x1's maximum value plus x2's maximum value will be equal to 5 centimeters. So now we'll see from that how we'll calculate x1 and x1's individual maximums. But if this was a single spring system, you can see that this is how the SHM equation would look like. The y as a function of time, which is the downward displacement of the block from the mean position, that would vary like this, like a minus cos omega t function. So y is the downward displacement from mean position. And correspondingly, x, the extension of the spring, that would look like this. So at half time, it would be at the lowest position. Krish, do you want me to scroll up further or this part only? Krish, did you want me to scroll up to the part above this or from here itself? Okay. So this is a little bit complicated, understanding the relationship between X and Y. Okay. X is the extension of the spring and Y is the downward displacement from mean position. So make sure you understand this. Okay. So mean position is the position where Y is 0, but X is equal to XE. Okay. Therefore, at Y equal to some general Y, X becomes XC plus 1. Okay. So this whole concept is explained in these two diagrams here. So make sure you understand this in detail and let me know if there's any doubt about this. Because there are a number of questions, types of questions which are based on this concept over here. So any vertical spring mass system, if you ask to calculate the time period, it's not so complicated. You have to just find the equivalent spring constant and omega square is k divided by m. But if you ask to find the amplitude, the equation as a function of time, the phase constant, all these things, then you have to take care of this part, that understand where the mean position is and what that mean position is with respect to the state of the spring, that is x of the spring. Okay, so let's now understand this in context of the individual springs, what is going to happen. So for that, you just need to compare the situations. Achha, you want to still write down this part? Okay. Okay, okay. Take your time, no problem. Okay, so Diti, hope you've completed this part. Now to understand the individual springs, how their maximum extension is working out. So if we compare the state of the system, initial state, let's say equilibrium state, and then maximum extension state. First, let's see for the equivalent spring. Okay, so for the equivalent spring, when it's starting out in the initial state, your x of the spring is 0, but the y of the SHM parameter is minus 2.5 centimeters, and starting from rest, but with maximum acceleration equal to g. So this is one extreme position. Now from here, when it reaches the equilibrium position, x becomes mg by k, where k is the equivalent spring constant. So at this point of time, the acceleration is 0, but the speed is maximum in the downward direction. At this point of time, this is, so x is equal to 2.5 centimeters, whereas y is equal to 0. This is a mean position. This is the extreme position. At the top. Okay. Now so basically you can see therefore that from extreme position to mean position, this is one amplitude. This displacement is an amplitude of 2.5 centimeters. Okay. But because it's having this maximum speed, it will go further down. And by the time it reaches one more amplitude below, now it will reach the lowest extreme. So at this point of time, it's at the lowest extreme position. So again, its velocity will be 0, but its upward acceleration will be maximum. So at this point of time, the spring's extension is actually 2 times xt, or 2 times mg by k, which is 5 centimeters. And the y coordinate is plus 2.5, or positive of the amplitude. Here it is negative of the amplitude. Okay. So hence you can see that this is the maximum extension. Now at this maximum extension position, if you actually see what is happening, the individual springs are like this. Okay. This is at L1 plus some x1's maximum value. This is at L2 plus some x2's maximum value. And the block is at rest, but having upward maximum acceleration. This is corresponding to this diagram. This third diagram is over here. And if you look at the first diagram, which is the upper extreme, and compare this with the state of the springs in the upper extreme, the individual springs, that was like this. So these were at L1 and L2 at this point of time. When again the block was at rest, but it had maximum downward acceleration. Okay, so if you compare these two now, you can see that x1 maximum plus x2 maximum is basically x maximum, which is 2 mg by k equivalent, or 5 centimeters. Okay, but also from this point you can see that now this point where they are joined, that point P is a massless point. So the net force on it must always be 0 at all times. So therefore, K1 x1 max is equal to K2 x2 max. So from this we can see that the ratio of x1 to x2's maximum values is the inverse of the ratio of the spring constants, which is basically how much? 12/6, right? So 2 is to 1. So x1 is to x2 is 2 is to 1, and x1 plus x2's maximum value is 5 centimeters. So from this now you can see that x1's maximum value will be 2/3 of, so that's 10/3 centimeters, and x2's maximum value will be 1/3 of x maximum, so that is 5/3 centimeters. So this kind of values they will have. Similarly, when they're at the mean position, you'll also see at the mean position, x of this equivalent spring is this. So x1 will be again 2/3 of x, so it will be 5/3 centimeters, and x2 will be 1/3 of x, it will be 5/6 centimeters. So this is like the complete analysis of this kind of system. This is more like a sort of JEE Advanced type of analysis, because we're doing a lot more than just finding the time period or finding the amplitude alone. Okay, now a couple of more things we will see here, which have not been asked in the question, but directly you can see from the above diagram. What is the maximum speed of the block? For that you can see B max is equal to A omega. That is when it is at the mean position. So here the amplitude was 2.5 centimeters into omega was 20 radians per second. So you can see that that is going to be 0.5 meters per second. This is the maximum speed of the block. Okay. And you can verify this by work energy method later. This is what we are getting by SHM. And also we'll talk about the maximum acceleration. Just note down this much first. Okay, so the final thing we'll understand here is that maximum acceleration of the block. Maximum speed was at mean position. Maximum acceleration will be at extreme position. You can see formula wise, the maximum acceleration should be a omega square. So it should be so it should be 10 meters per second square. You can also understand from the free body diagram from FBD at the upper extreme. X of the spring is 0. So there is only mg acting on it. So this acceleration should be equal to g. Whereas if you talk about the lower extreme, the lowest point, x was the maximum extension, which was 2 mg by k. So the spring force will become twice the weight. So you can see that this maximum acceleration that also shows us that our calculation of omega and amplitude is correct, because the free body diagram, which has nothing to do with SHM, which is just Newton's law application, is giving us the same result for maximum acceleration as we are getting from the SHM parameter. That maximum acceleration has a magnitude of amplitude into square of omega. So this is another important aspect of this particular type of question. Okay, so this is all about our vertical spring mass systems and in general.
Sir, just a minute.
Okay.
Sir, can you please scroll it up a bit just for a minute? No.
Just a moment.
Yeah.
Yeah, which part the diagram? This part?
So yes, just a minute.
Right.
Sir, done, sir.
Done. Okay. Right. So now you have seen all the variations and possible type of calculations, etc., that you have to do for spring mass systems. Okay. So now we move on to the next part of SHM, which is basically angular harmonic motion. So if any system has a situation where you have, let's say, any anything like a rigid body which has an angular equilibrium position. That means at this equilibrium position, the net torque is zero about a fixed axis. And from this equilibrium position, if we take the system to any angular displacement, so we have rotated the system from the equilibrium position to some angular displacement theta, then it should have a tendency because of torque to come back. So there should be restorative torque when given an angular displacement from the mean position on either side. So there is restorative torque tau when displaced by angular displacement theta from the mean position. So this position becomes our mean position. Then such a system performs what we call angular oscillation. That is, it will have a to and fro angular motion with respect to mean position with fixed time period. So such a system performs angular oscillations. That is, to and fro angular motion with respect to the mean position with definite time period and amplitude. Now, if such an angular oscillation happens to be harmonic, if such an angular oscillation is sinusoidal or harmonic with respect to time, that is, the angular displacement at any point of time is E sin omega t plus phi, where omega again becomes 2 pi upon time period, then it is called the angular harmonic motion. Or in short, we sometimes just call it angular SHM. So this is the theory of angular SHM. Now, from this, we will see the condition for angular harmonic motion in the same way like we had seen. So basically, like we had seen in linear motion, for linear oscillation, the condition is that there should be a mean position where net force is zero. And when we displace on either side with respect to the mean position, there should be restorative force. So a system, a linear system with mean position and restorative force, it does linear oscillations with fixed time period and amplitude. But if this oscillation is harmonic, then it is called a simple harmonic motion. It's called a simple harmonic motion. So like that now, if we have an angular system such that it has a mean position where the net torque is zero, but the moment we displace it from that mean position, we get some restorative torque, then such a system is capable of oscillating angularly, that is oscillating with an angular motion, with an angular amplitude, an angular displacement with respect to the mean position. They have fixed time period and amplitude. And further, if that angular displacement with respect to time is periodic in such a manner that it's a harmonic function, then we call it an angular harmonic motion. So it is the angular version of simple harmonic motion. Instead of motion along a straight line, which is harmonic with respect to time, it is angular motion with respect to a fixed axis, which is harmonic with respect to time. Okay, so now let us understand the dynamical condition for angular harmonic motion. So this, yes.
Excuse me, sir. Sir, can you please scroll it up? I mean, the right hand side part is not complete. Done, sir.
Okay. So here the only thing to keep in mind is that E is angular amplitude. So it's in radians. A is equal to the maximum angular displacement because theta is angular displacement in radians. Rest of the things are the same. Now from this we get angular velocity as a function of time by differentiating, and angular acceleration so this is angular acceleration, and we can see that angular acceleration has the relationship with angular displacement. This is the dynamical condition or the net torque Okay, so this is a dynamical condition that there is restorative torque whose magnitude is proportional to angular displacement. Just like in condition for SHM, we had restorative force whose magnitude was proportional to linear displacement or translational displacement. In angular SHM, we have the condition that there should be restorative torque whose magnitude is proportional to the angular displacement. Okay, so let us now look at the primary example of angular harmonic motion, which is going to be the case of the physical pendulum, or it is also called compound pendulum. As in your module, it is called compound pendulum. You'll see that for small amplitude oscillations, that is the angular displacement, sorry, the angular amplitude should be a small angle. Less than about 5 degrees. It performs angular harmonic motion. So let us see the structure of a physical pendulum. So basically, a physical pendulum or compound pendulum can be made by any rigid body. Which is having a hinged at P, such that it can rotate freely about a fixed horizontal axis at the point P. So it can rotate freely about this kind of an axis. And the center of mass of the rigid body is, let's say, the point C. M is, let us say, the mass, and I is the moment of inertia about the axis at P. And also one more important parameter is D. D is the distance between, just a moment people, I'll have to reshare the file. Yeah. So D is the distance PC from the center of mass to that. Okay. So these are the parameters we will require to find its time period and find the condition for angular harmonic motion. But this is the physical structure. Okay. Physical design like this. So now next we will see that based on these parameters, M the mass, I the moment of inertia about the axis at P, and D the distance of the center of mass from the point P, we can find the time period. And first of all, we can derive the condition that it performs angular harmonic motion when given small angular displacement. For very large angular amplitude or displacement, it will not be a harmonic motion. It will still be an oscillatory motion, but it will not be harmonic. And we'll understand that once we derive those equations. Okay, so now let us I'll take 5 minutes more to complete this portion. So very simple derivation it is. So you can see that when your center of mass is directly below the point P, the torque is zero because mg's line of action is passing through P. So torque is zero, so this is the mean position. But the moment we take the rigid body to an angular displacement with respect to this vertical line. Okay, so now let's say with respect to this vertical line, I've taken it to an angular position where the center of mass is now here. So the line PC is now at some angle. The whole body has been given an angular displacement theta. So you can see that mg is now creating a torque. It's creating a restorative torque. And that torque you will see, if we calculate it, it's force mg which is acting like this. So about the axis of rotation, which is at the point P, the moment arm is this distance. This distance. So if this angle is theta, so you can see that this distance will become d sine theta. So this torque will be equal to mg multiplied with d sine theta, and that is equal to I alpha. Now alpha you can see will be minus of d2 theta by dt square because alpha is opposite to theta. The diagram you can see that theta is a anti-clockwise displacement and the angular acceleration is opposite that. Okay. So we can write that minus I into d2 theta by dt square is equal to mg d sine theta. So you can see that we don't quite have the angular harmonic equation because the proportionality is that d2 theta by dt square is equal to mgd divided by I, but into sine theta. But for small angular displacement, sine theta can be approximated as theta. So we have so this is your angular harmonic equation. With omega square as this. So it performs angular harmonic motion under the special condition. For the condition of small amplitude, so time period which is 2 pi by omega becomes this. So this becomes like a general formula, just like we had a general formula for spring mass systems. The time period is 2 pi under root m divided by equivalent spring constant. So for any physical pendulum, this becomes a general formula. So as you're noting this down, you can also see a special example of this. Example, if we have a simple pendulum that consists of a thin rod which is having a hinge at the point P. Mass m and length L. So you can see that the center of mass is over here. So for this case, we will substitute D as L by 2, and I is moment of inertia about T, so that is one end of the rod, so it is ml square by 3. So for small angular amplitude, it performs harmonic oscillations with time period. So this becomes the formula for time. And to go back and forth like this. Okay, so in the next lecture, we will see the numerical examples of physical pendulums of various different shapes, like this being the simplest shape, a thin uniform rod as a physical pendulum. So ultimately, there'll be a little bit of application of rotational mechanics to calculate moment of inertia and center of mass concept to calculate the distance d from the center of mass to the axis of rotation. But the rest, we can just directly apply this formula. Okay, so with that, we complete today's session. Wish you all the best and happy Ganesh Chaturthi to all of you. Okay. I know with the pandemic, yeah, it's a very low key festival and you're not probably allowed to visit the pandals, etc. But all the same, enjoy the festival and wish you all the best till next time.
Bye, sir.
So just a minute.